So the goal of this video is to run some simulations in order to think about coverage properties of confidence intervals. So simulations are interesting because the goal in a simulation is to act like we actually know what the population parameter of interest is. But remember, in the statistical context, we don't know what that thing is, and that's what we're trying to estimate. So simulations are actually really nice for helping us think about the properties of certain statistical methods. And then once we know those properties, we apply them to contexts where we have data and we don't really know the underlying properties of the population. So let's think about a simple example where we have a normal population and we take a sample, an IID sample from that normal population. So let me start out with X, where X will be our sample from a normal distribution. So our norm generates random numbers from the normal distribution. And let's generate, we'll do n numbers where n is our sample size. Let's make it sample size 50. And if we don't specify the mean and the variance, it'll come from a standard normal distribution, or we could always specify 0, 1 as the defaults, or if we wanted to, specify 10 as the mean, that would work also. So the result here should be 50 numbers from a standard normal distribution. And if we wanted to look at a histogram to see, does it look relatively normal? Well, it's only 50 numbers, so it looks, well, not that great. Of course, if we increased it to 500, it would look quite a bit better. But we'll stick with 50. And what I'll actually do is set the seed so that we generate the same random numbers each time. So we'll get these same numbers in all these samples. Now, in class, we learned how to calculate a confidence interval. And what I'll first do is calculate that confidence interval just for this single sample. So the confidence interval required x bar, so the sample mean. So x bar for us is just the mean of x. And in the case where we don't know the population standard deviation, let's imagine that we don't know it. So we will estimate it using S, which will be just the sample standard deviation, and R has a function for that. It's SD. And then the confidence interval will be a lower bound and an upper bound. So in R, the function C, I think it stands for like concatenate, so it takes two things and puts them together. So C of x bar minus, let's do a 95% confidence interval, so 1.96 times S divided by the square root of n. So that's the lower bound. The upper bound will just be x bar plus that quantity. And then we can print out the confidence interval. And we see in this case that the confidence interval, the lower bound is about -1/2, and the upper bound is 0.07, 0.08. We see that we do have coverage of 0. So in this case, we did get coverage of what we know the true parameter to be. But of course, when we calculate a confidence interval and we don't know the true mean, we won't know if we actually have coverage. But what we do know is that the procedure that generates confidence intervals gives us coverage most of the time, where most is 95%, 99%, 90%, whatever you set the confidence level to be. So how could we check that coverage? Well, one thing that we can do is not just generate one sample, as we did here, but modify this to generate many, many samples. So let's generate 1,000 samples. And the way that I'll do this, you could write some loops if you want to. R is really nice in that it allows you to avoid writing loops. And in this case, I'll use the replicate function. And what I want to do is replicate something many times, in this case m times. And I want to replicate generating a sample of size n from a normal distribution. So let me comment out some of these things and show you what we get here. So x now should be a matrix. So dim of x will tell you the dimensions of x. And it should be a matrix. And the matrix will have 50 rows and 1,000 columns. So we can interpret every column as a different sample of size n equals 50 from the normal population, in this case a normal 0, 1. So we just have to modify a few things if we want to calculate many confidence intervals. One of them would be this line here. So if you take the mean of what is now a matrix, it'll just give you a single number. But what we want is the mean of every column. Well, to get the mean of every column, there's a function in R called colmeans, and that will give us the mean of every column. And if you wanted to make sure it's of the right size, well, there the length of x bar gives you a vector of size 1,000. And that means we have 1,000 sample means, one sample mean for every sample that we've drawn from this normal distribution. So it would be great if there was a function called col standard deviation or something in R, but for some reason there's not. So we kind of have to find a way to compute the standard deviation of each column. And luckily there's a function called apply that allows us to apply a certain function either to the columns or rows of a matrix. So what this line will do says apply the standard deviation function to the columns, so 2 is columns, 1 would be rows, of the matrix X. So again, if we did the length of S, we should get a vector of size 1,000, each one being the standard deviation of the column of X. So now that we've modified the way that we compute means, so we can get a mean for each column of our matrix, and similarly a standard deviation for each column, the next step will be to compute the confidence interval and make a slight modification to the formula that's here. So right now this C will just concatenate these numbers, so it'll be one long list. But really what would be nice is to have a matrix that has 1,000 rows and 2 columns, and each row will be the lower bound and the upper bound of the confidence interval. So the function cbind will do exactly that. And if we just want to look at the first few confidence intervals here, we'll print the head, and we'll notice that, well, okay, this first row looks like a lower bound for a confidence interval and an upper bound, and same thing, lower bound for each one of these, upper bound. So the 6 confidence intervals that we've computed here, each one for a separate IID sample from a standard normal distribution, each one of these looks like it covers 0. So we know that about 95% should cover 0, and it looks like the first 6 that are computed cover 0. So now that we've computed the confidence intervals, let's check the coverage. So in order to calculate the coverage, we basically want to see, is the lower bound greater than 0, or is the upper bound less than 0? So the way to code that would be, in the confidence interval, for any row in the first column, are we greater than 0? If so, give me a true. If not, give me a false. Or, in the confidence interval, any row in the second column, are you less than 0? If so, true. If not, false. And then if we sum over this vector of truths and falses, we should get the number of true values. And then if I divide that by m, the number of samples we've taken, we should get the number of confidence intervals that don't cover the true parameter mu equals 0. And then if we want the actual coverage, we should do 1 minus that sum. So we see the value that we get is just a little bit under the stated coverage. It's about 93.1%. And there are maybe two different reasons for that. One reason is that the number of simulations we've done is 1,000. And so the coverage property is really about sort of an infinite number of simulations. So if we were to increase m, we should get something a bit closer. Yeah. The other issue is that we have a sample of size 50, and we're relying on a convergence and distribution result because our statistic that we use in the confidence interval relies on S. So it relies on an estimate of the standard deviation and not the true standard deviation of 1. So for a small, I mean, this is not a terribly small sample, but a smaller sample will give more variability in your confidence interval, which means the coverage won't be as close to as stated, so it's approximate. So if we increase the sample size, we might see, again, a coverage closer to 95%, whereas when it was just a sample of size 50, it was around 93%. So I hope this video gives you a sense of how to run a simulation to check the coverage of confidence intervals, and to note that for confidence intervals there are approximate coverage when you replace the standard deviation with an estimator, and the more simulations we do, the closer we'll get to the stated confidence level.